Swayam Prabha. Digital India. Educated India.
Now, there are multiple ways by which I can construct this I section. Okay, say I am making this I section from 3 plates, or I can make the I section from 5 plates. Okay. So, there depending upon how you build up this I section, you have to use the appropriate shear stress. Okay. Now, let us say the I section is made like this. I have a plate which runs through the entire depth of the I section, and I have flanges coming out like this, and I have welding it and say I am welding it here and here. Now, how will this I section fail? This I section will fail because the web flange interface is going to show a differential motion like this. Okay. So, this is nothing but sigma xz shear is what this weld should resist. Okay. This is the weld, these are welds, and this weld should resist sigma xz shear. This is gone by sigma xz shear governs the weld design. Okay. In contrast to this, I can make a I section like this, or I have a through plate for the flange, a through plate for the web, and a through plate for the bottom flange too. Here again, now I am going to weld at this interface. Now, what shear stress governs the design? The shear stress that governs the design here is sigma xy shear governs the weld design or the connection design. Okay, it can be nailed also. Okay, because in this case I have the web and flange sitting like this. When there is a differential bending, this flange is going to slide off like this. Okay. So, this is basically going to produce a shear sigma xy shear. Okay. This sliding is going to provide a sigma xy shear, because x is along this direction of the force, y is perpendicular to the web surface on which this flange is moving. Okay. This produces a sigma xy shear stress. Okay. So, the web has to be designed, the weld has to be designed for sigma xy shear stress. Now, which one of these would you prefer in a design? If I want to economize on my welding depth, then which one would you prefer? Now, what is the maximum sigma xy shear stress that comes at this interface? So, you have to design for a shear stress of, let us go back a slide, tau 1 is Vy by Izz into Bf into H plus Tf by 4. Basically, we are looking at this tau 1 value, that tau 1 value is given by Vy by Izz into Bf into H plus Tf by 4. Okay. So, the value here is Vy by Izz into Bf H plus Tf by 4. Okay, that is the shear stress that the weld should resist, whereas here the shear stress that this weld should resist is given by this expression in here, maximum shear stress at the web flange interface is Bf by Tf into sigma xy of the top flange, or Vy by Izz into Bf by Tw into Tf into H plus Tf by 2. Okay. So, let us write that. Izz to Bf by Tw to Tf to H plus Tf by 2, right. Okay. Let us say this is xz, y xy. Now, what is the ratio of sigma xy by sigma xz? That will be Tf by Tw 2 times that, right. Okay. So, typically Tf by Tw will be greater than 1. So, you can see that if Tf is greater than Tw, sigma xy or tau xy is greater than tau xz. So, you want to design, if your weld strength is critical, you have to design it as this, because this will require less amount of weld depth compared to this design. Okay. Now, let us say I am not interested in welding it, but I am interested in nailing this I section. Like this, I am going to build up a I section from wood instead of steel. And I have a nail which goes through like this. Okay. I have a nail which goes through like that. In the top view, this is y and z, and if I plot the top view, which is x and z. Okay. Now, this nail would be positioned at some regular intervals. Say the spacing between the nails was S, and I am interested in finding out what should the spacing be, given that the shear strength of a nail is tau max. Okay. So, and the area of the nail is AN. Okay. Now, I am interested in finding what should be the spacing of this nail, so that it can withstand the shear stresses that are coming on that section. Okay. So, here as you see, it has to withstand sigma xy stress. The nail has to withstand, because the flange is going to slide like this, the nail has to withstand the sigma xy stress. Okay. And the sigma xy stress at that interface is given by Vy by Izz into Bf from here, Bf by Tw to Tf to H plus Tf by 2. Okay. Now, this shear stress into S into Tw, that is what we are saying is, here the web is like this, this is Tw. Okay. So, this nail should withstand whatever stress comes in this region, this distance is S. I am assuming the nails are uniformly spaced. Okay. And hence I am assuming that S by 2 is this distance is S by 2, and this distance is also S by 2. Okay. So, the net distance is S and the net area is this entire area, that is S into T W. Okay. This should be resisted by tau max into area of nail. Okay. So, the entire shear stress that comes, shear force that comes in that area has to be resisted by that single nail there. Okay. So, A into A n. Now, I know A n, I know tau max, I know the cross sectional dimensions, I know V y, I z z and all those things. So, from here I can find what S is, the spacing of the nails I can find from here. Okay. So, as we saw in the previous lecture, if I did not have this nail and if I add just the plates place one top of the other, there will not be integral action and hence there will not be there will be separation of the surfaces between the web and the flange, and hence it will not resist the load as you want to resist unless you design the connection properly. Okay. So, that is the reason why you have to find the shear stresses, and that is the reason why you have to design the connection to resist the shear stress that comes on that section appropriately. Okay. Now let us look at the equilibrium of forces and moments due to the shear stress distribution at a section. Okay. So, I have an I section, okay. I have an I section. So, the flange width along the two directions were the same. Okay. So, basically what will happen is I add a shear flow like this. Okay. So, this was Bf by 2 and this was Bf by 2, and these two horizontal forces cancels out each other, they will be of the same magnitude, as does the horizontal force on the top flange here on this side and on this side. Okay. And the sum of this vertical shear stresses would integrate to give you Vy, that is integral sigma xy d Ax would give me Vy. Okay. You can show that, I am not going to show in this course, but you can integrate the expression that we got for sigma xy, integrate this dAx is dy dz, you can integrate and you can see that it will lead to Vy. Okay. Now, let us look at, so the first equilibrium is satisfied. Okay. Now, let us look at the moment equilibrium. Okay. The moment equilibrium, what happens, there is a net horizontal force here, say this is Q1, there is a net horizontal force of same magnitude Q1 on this side. Okay. So, what is this going to do? This is going to produce a clockwise moment. Okay. This is going to produce a clockwise moment. Similarly, there is a net force, this will also be of magnitude Q1 acting like this, Q1, there will be a net force Q1 acting like this and a net force Q1 acting like this. Now, these are again balanced forces separated by a lever arm, this produces a anti-clockwise moment of the same magnitude as the clockwise moment that was produced by these shear stresses, by the other shear stresses, right. So, what will happen is, now this section there is no torsion, net torsion in this section, this moments that is generated due to this Q1 being separated by some distances, a moment along the axis of the beam. Okay. The moment that this Q1 generate is along the axis of the beam, and then those are torsional moments. In this cross section, since all the forces were equal and supported by the same lever arm, the torsional moment, net torsional moment is 0 for this section. But there are sections where this will not happen, and in the next class let us see what happens for those sections. Okay. So, in the next class we will see what happens to those sections where there is a net torsional moment coming in because of the shear stress distribution. Okay. Thank you.